All right, the next section that we have is 16.5. Here we're moving on to surface integrals of vector fields. So, the main difference here between what we were doing in 16.4, which were scalar surface integrals, here these are vector surface integrals. So, for a vector surface integral, ultimately what we're trying to do is, we can think of it like this. Let's say we have some sort of surface. Something like that. There's some surface. If you want to, you can kind of imagine it. I'll draw some grid curves on it. Okay. Something like that. So on these grid curves, so this is some surface S. Okay. And let's say we're interested in this visible side of the surface. So that's the side that we care about. So let's go ahead and orient this like the following. I'll put a normal vector on here to orient the surface. Okay, so there's our surface S. So let's imagine now that there's a vector field flowing in this region of space. Okay, so here's some field lines that I'm just drawing surrounding the surface. Okay, so now these field lines, I intentionally did not draw any directional arrows on these because I don't want to do that yet. But this surface, if this is here in the midst of this vector field, then these vector field lines will come and they will strike or pierce the surface S. And if we think of these vector field lines as maybe electric field lines, then they can permeate through things. So let's just assume that that's going to happen here. And the way they're going to there's two things that are going to happen. When a field line comes into contact with the surface, it may go underneath the surface and then it will poke back out above the surface. In which case the flow, let's just say it's flowing this way, left to right, kind of. Okay, so there's a field line. And let's say this one kind of does the same thing. This one, and maybe it connects to that one, so then we get this field line like that. Okay, so this goes under, pokes up through, and let's just say this one just kind of misses it. That's fine. So let's just kind of decorate some of these with some orientation arrows. Okay. Now there might be other regions, so maybe in a particular, somewhere in between here, at some point these vector field lines, maybe they do the following, where they come in and then they go underneath. So the field line actually, at some point in between here, it goes underneath, pokes back up through, and then over here, it's above, pokes through, and then comes underneath. So that can happen. That can happen. The vector field can twist and twirl and curl and things like that. So maybe that's what's going on over here. We've got another one that kind of does this, and then this does something like that. Those are all very plausible vector field lines that can happen. So now on this surface S, we see that in some regions, the vector field tends to be leaving the surface, much like this normal vector is based on the top, let's say, and leaving. Where some, it tends to be the opposite. Here, the field line is entering the surface on this side and then leaving or exiting the surface on the underside that we can't see. So this blue vector, this normal vector here, this is an arbitrary choice. We're allowed to think of our surface as, we can orient it with a normal vector on this side, or we could orient our surface with a normal vector maybe coming underneath of it. That's fine too. But when we make this specification of the normal vector, what we're actually doing when we calculate a vector surface integral up here is we're checking to see at every single point on the surface, at every single point, we want to know what is the amount. So I'm going to say in kind of in parentheses or in quotations here, the amount of the vector field going through the surface in this direction. Okay, so really coarsely, at this location, let me label these. I'll call this location. Let's get something else here. Let's do this in green. So we've got a location A, a location B, and a location C, and a location D. So at all these locations, what you can imagine is if we zoom in really close here. So for instance, let's zoom in. If we zoom in really closely, then our surface S at a location A, so let's call this point A here, this is zoomed in. Well, if you zoom in on something, and you zoom in really closely here, even though that this surface is most certainly curved, when you zoom in sufficiently close, a curved surface is approximated by its tangent plane. So if we zoom in on the point A very close, then eventually the surface S looks like its tangent plane at this point A. So at this point A, we have a normal vector, which is definitely going to be something like this. So there's our normal vector. I'm just going to call this N. And over here on the actual picture of the surface, our normal vector, maybe it's doing something like that. There's our normal vector. And then you can see that the field line is exiting not exactly the same, but it's sort of creating this angle here, this acute angle. So let's go ahead and draw my field line in red over on this zoomed in version. So, oops, let's go ahead and, there you go, something like that. So there's the field at this point A. So at this location, there is some angle. So we'll call this angle theta. So here we can see that theta is acute. So what we want to know is at this location, and not just at this single location A, but we want to do this process at every single point. So over the entire surface, all infinitely many points in this surface, we want to do this process. For each point on the surface S, we take a look at what the normal vector is at that point, and then we take a look at the vector field that pierces, or the value of the vector field at this location. That gives us a pair of two arrows, the vector field line F and the normal vector N. With these two arrows, we can definitely talk about the angle between them, theta. And what we're going to do here is we can take a look up here at the definition of this. This is doing this composition. So what does this composition right here tell us? This essentially is telling us, look at a location on the surface, because that's what R is, right? R is a surface parameterization. So this R of UV is just a way of more conveniently describing the surface S in more familiar terms. So this is really no different than just the vector field, but we're choosing to describe the vector field, we're restricting it. Effectively, we are restricting the vector field to the surface. So this is the vector field on the surface. So let's write that. So this is the vector field on the surface S. And what's this? this is the normal vector to S. So at a point A, this right here is exactly, more specifically, this is f of r of uv. And then this n here is going to be this or rv cross ru. Because remember, the only difference in this order versus this order is whether or not our vector is pointing in this direction or if it's pointing downward. Okay? So let's say for this example, this upward direction is given by this order. Okay? Let's just assume that. But honestly, it depends on the problem. It doesn't matter which order, as long as you are consistent in your problem and you're following any instructions that your problem may specify. So then, what's going on between these two quantities? The red vector and the blue vector, what's happening? We have a dot product. And remember that for a dot product, there's another way that we can calculate a dot product. For a dot product, we can also say, okay, let me erase this theta as acute for a second. We'll come back to that. In general, f of r of uv dotted with some vector. Actually, let's make it more simple. Given a vector, let's say, a vector v dotted with w. This is like a chapter 12 result. Chapter 12 tells us that v dot w is equal to the magnitude of v times the magnitude of w times the cosine of the angle theta between them. So if we apply this information to the vector f of r of uv, this is one vector, dotted with another vector, let's say ru cross rv, which we can just say n, right? This is just n. All right, we're just giving it the nickname here. Then this is equal to the strength of the vector field at this point on our surface, dotted with this normal vector, times the cosine of the angle theta between them. Oop, not dotted with. This should be magnitude. My apologies. Magnitude. Okay. So, basically what this is doing is it's taking the strength of the vector field, the length of this normal vector n, which we can assume in this case is going to actually be 1. This is not supposed to be a proof, but ultimately I want us to just think of it in this way. So we can think of it as the strength of the vector field. I'm going to omit the r of uv because we know that we're only talking about the field on the surface. So we'll just omit that. This is the strength of f times the cosine of theta, where theta is the angle between the normal direction to the surface and the field line itself. It's this angle. Well, clearly you can see that so as we have in the above picture, if theta is acute, then the contribution to the integral The contribution is positive. Now, if we think about this, when is the contribution to the integral going to be the greatest? Greatest is when the cosine of theta equals 1, which implies this happens if and only if, since theta is an angle between 0 and pi, this happens if and only if theta is 0. So the biggest contribution we get to the integral is when the field line is exactly in the same direction as the surface. So you can think of this surface integral here. What it's doing is it's calculating how much of the vector field is flowing through the surface in the normal direction, right? So the maximum contribution comes when the red field line is in the same direction as n. Smallest is when the cosine of theta, I'm going to say smallest in quotations, because it's going to be when cosine of theta equals -1. And this happens if and only if theta is pi. So this would happen if the field line were actually going through in the opposite direction. Then we would subtract the strength of the vector field. And then it is 0 value when, of course, theta is pi over 2. That would be when the vector field line isn't actually going through the surface from one side to the other. It's perfectly parallel to the tangent plane at the point. So a surface integral is really much like a line integral, it's the weighted sum of the vector field. It is the net flux. It's the amount, in quotations, of the vector field through the surface in a specified direction. So on the surface over here, if on the surface we say that this is the, let's say, top surface, when we make our declaration of our normal vector to be this, we are saying we are interested in knowing how much of the field actually enters from the bottom and exits through the top. Now, on this arbitrary surface, an arbitrary field I drew, at the point A, it exits through the top. At the point B, it exits through the top. But at the point C and D, the field actually enters in the top and exits through the bottom. So it seems like we're going to have positive contributions over here at A and B to the surface integral, where over here, because the angle theta at these two values is obtuse, we're going to have a negative contribution here. And since everything is continuous here, we know that if there's going to be if the angle over on this side is acute, the angle over here is obtuse, that means somewhere in the middle here, somewhere in this area here, there's got to be a location where the vector field actually switches directions, something like that, where it means maybe it just grazes the field right here. It touches the surface at a certain point, but it doesn't actually go underneath of it or come from underneath and exit above. It's somewhere right here where it's actually perfectly parallel to the tangent plane at this location on the surface. So that is exactly what what flux is. So in this problem, flux is the net flow of the vector field through something in a certain direction. So here the direction is just an arbitrary specification. Whether or not are we interested in seeing how much of the field goes in this direction, from the bottom through the top, or in the opposite direction perhaps, from the top out through the bottom. Doesn't really matter a ton, but it will change the answer by a plus or a minus sign. You'll have opposite answers depending on how you choose to orient your surface.